When we think of a scientific model, we imagine a perfect miniature of reality. We assume the highest achievement of simulation is absolute, physical precision. In professional terms, this is the assumption of isomorphism, the idea that a model is only valid if every element and structure maps perfectly, one-to-one, to the real world. Yet, the foundational thinkers of system dynamics rejected this completely. As the pioneering cyberneticist W. Ross Ashby accurately pointed out, every model is inherently inferior, a distortion and a lie. Consider the bedrock equations of classical physics and biology. The ideal gas law ignores intermolecular forces and the actual volume of molecules. Population genetics relies on isolated populations that do not exist in nature. Mechanics hinges on the mathematical concept of frictionless planes and point masses. These deviations are not the result of poor measurement. They are deliberate, mathematically convenient falsehoods. If scientific progress relies on systems that intentionally warp reality, how does it reliably produce objective truth? The answer requires a shift in how we evaluate information. A model's epistemic value, its capacity to generate verifiable knowledge, does not stem from how closely it mimics the physical world. It comes from how ruthlessly it distorts that reality to serve a specific pragmatic objective. For decades, philosophers relied on a dyadic view of modeling, a direct relationship where a target system projects its properties onto an abstract model. But this framework breaks down under scrutiny. It assumes models are passive mirrors of nature, independent of human intention. To correct this, philosopher Ronald Geer proposed a triadic relation. Modeling is an active operation. A specific user utilizes a model to represent an aspect of reality, entirely framed by a defined purpose.
Under this definition, creating a frictionless plane or an ideal gas is the correct engineering choice. Those unrealistic assumptions are strictly justified if they satisfy the operational conventions of the scientific community using them. Models are built tools. They are epistemic artifacts designed to actively mediate between the rigidity of pure theory and the messy complexity of raw data. The philosopher Nelson Goodman codified this by focusing on denotation. He argued that for an object to represent another, it simply needs to stand in for it. Physical resemblance is neither required nor sufficient for representation. To see how this works, let's deconstruct a famous epistemic artifact. This computer-generated DNA molecule operates using multiple layers of denotation. The first is straightforward resemblance. Its spatial geometry accurately mimics the physical double helix shape. The second layer is isomorphism. The pairing between the specific nucleotide couples in the visualization structurally maps to the rigid chemical bonding rules of the real molecule. But the third layer relies on pure, arbitrary symbolism. The brightly colored shaders used to differentiate the chemical elements have zero relation to physical reality. Carbon and oxygen do not possess red or blue colors at the atomic level. By fusing structural isomorphism with entirely invented symbolism, the artifact intentionally strips away the overwhelming complexity of quantum mechanics, allowing the human brain to successfully process the genetic code. An even purer proof of this concept emerged in 1735 with the Seven Bridges of Königsberg problem. The challenge was to map a continuous walking path through the city that crosses every single bridge exactly once. Attempting to calculate this route using a geographically accurate map of the city rivers and streets immediately causes cognitive overload. There are simply too many physical variables competing for your attention. The mathematician Leonhard Euler solved the problem by taking the opposite approach. He didn't calculate the path by adding physical detail. He achieved clarity by aggressively destroying spatial data. Euler invented a topological graph, an abstract format that discards physical distance, prioritizing pure connectivity. Sprawling landmasses are crushed down into single, dimensionless point vertices, labeled A through D. The bridges are similarly reduced to simple connecting edges. By annihilating irrelevant properties like the exact length of the bridges and the geographic shape of the islands, Euler rapidly proved the walk was mathematically impossible. In doing so, he invented the field of topology, proving that strategic omission generates epistemic clarity. While the visual topological graph is excellent for human pathfinding, it is highly inefficient for complex algorithmic calculation.
For programmatic calculation, that exact same topological data can be restructured into an adjacency matrix. This alternative format arrays the intersections of the vertices into a rigid grid, converting the bridges into purely numerical values of zeros, ones, and twos. Both the visual graph and the mathematical matrix contain the identical structural truth of Königsberg. The difference lies in computational efficiency. The format dictates how easily the embedded data can be manipulated. This highlights cognitive affordance. A spatial model invites tactile manipulation. A numeric matrix invites automated processing. Changing a model's medium does not alter the underlying system it represents. It simply restricts or expands the specific actions its user is permitted to take. We continually translate reality into these abstract formats because executing direct calculations on physical systems is frequently impossible, dangerous, or financially ruinous. This chart shows Ross Ashby's cybernetic framework. It maps the precise mechanical operation of how a dynamic model actively bypasses physical reality. The top axis represents the real-world target system, moving over time from an initial state, S1, toward a future state, S2. To predict S2 without waiting for it to happen, we initiate the first operation, encoding. We strip away the physical reality and translate only the critical variables downward, establishing the artificial model state, M1. The second operation is computation. The model runs its simulated parameters, safely accelerating the artificial state to its logical conclusion at M2. The final operation is decoding. The resulting data from the model is translated back upward to accurately predict the actual real-world outcome, S2. Cybernetics dictates that a model's worth is strictly measured by the reliability of this three-step shortcut. If the decoding accurately predicts reality, the visual realism of the model itself is completely irrelevant. In 1973, the German cyberneticist Herbert Stockowiak unified these concepts into a rigid architecture, establishing three mandatory pillars required for any functional model. The first pillar is representation. A model must intentionally stand in for a target system, even if that target is an unbuilt prototype or an entirely abstract concept. The second pillar is reduction. A model must consciously exclude the vast majority of the original target's attributes to maintain computational viability. Crucially, models also contain superfluous attributes. These are elements actively injected into the model that do not exist in reality, but are absolutely required to make the simulation function. The final pillar is pragmatism. A model is never a universal copy. It is built as a highly specific substitute for a designated user operating within a restricted time frame to execute exact operations. Attempting to evaluate any mathematical, computational, or visual model without clearly defining these three structural parameters is a core engineering failure. We naturally crave accuracy, but the belief that scientific progress requires a perfect one-to-one replica of the physical world is a cognitive trap. Consider the ultimate thought experiment, a map of a city constructed at a perfect one-to-one scale, detailing the location of every single atom of concrete and steel, offers absolute physical truth, and it is entirely useless for navigation. To comprehend the overwhelming, chaotic complexity of a real system, you are required to construct an artificial artifact. The mastery of modeling is not determined by knowing which precise points of data to include. In the end, to truly wield any model effectively, you must know exactly what it was brilliantly designed to ignore.